All right, class. I decided I'm going to make a couple of videos to help us think about AC circuits. Okay, so to start off with, right, we went from DC power sources to AC power sources, and really the difference here is, that in one of these you have a, relatively constant current with a constant applied voltage, and then the other one you have one that can vary over time, right? And so we kind of define these with different sine waves, and there's a lot of different ways to kind of look at these things and to think about how they're working. You did a reading where we looked at a little bit of the calculus that kind of lives behind this. So for example, we could say that, okay, if I have let's say a basic circuit that has an AC source, and I take that and I connect it across a capacitor, we can kind of model how the circuit is going to respond, right? The voltage applied to this thing, we could say, so this, it's not going to be a function of time, right? It's not some constant value. So the voltage is going to be some peak voltage value, right? Or the amplitude of this original signal that I have times something that'll make it vary over time. So a sine function works well for that. So a sine omega t. And the frequency of oscillation is hiding inside of omega. So sine of omega t plus phi, some like starting, phase angle, right? Where am I starting at? Am I starting at 0? Am I starting at 2 pi or pi or, whatever, right? Where am I starting in terms of phase? And so now I have some function that kind of defines how my voltage is changing over time. And then one of the things we want to know is, well, okay, so if this is how the voltage is changing over time, well, then how is the current changing over time, right? And with this, the current in our DC circuits, we didn't have to worry about this, right? You had an applied voltage and that generated a current in the circuit, and things didn't change, right, over time. But now they do, and so we need to see, okay, well, what is this relationship? And so one of the ways to do this is to say, okay, well, I have this capacitor here, and so what is this thing doing over time? Well, I can define the amount of charge, or Q, right? The amount of charge that's held on the capacitor is just the capacitance times the applied voltage, right? So there's that V, and then we can look at this and say, okay, well, I know that this value isn't constant, right? We know that it's changing over time, and so if something is changing over time, like, why not take a derivative, right, to define the little change? So I take the derivative of the charge with respect to time. So I'm going to do the same thing over here. So I'm going to take the derivative of this thing with respect to time. And now, I've got a couple of things that I can see here. So I look at this piece. So dq dt, or a changing charge over a changing time. Well, that is current, right? So now here's my current, and that's going to be equal to, well, so the C part of this is a constant, so I can pull it out in front of the derivative. So now I'm taking the derivative of the voltage, which is the peak voltage times the sine of omega t plus phi, with respect to dt. So now I just need to take the derivative of this thing with respect to dt. And again, the peak voltage is a constant, so that's gonna come out front. So we're left with the current. We're left with the current being equal to the capacitance times the peak voltage, and then when I go to take the derivative of sine omega t, So I look at it, I take the derivative of the thing inside of here with respect to t. Phi is just a constant, so it goes to 0. And so omega t, the derivative of that is just omega, so the omega comes out, right? And now what I have, and then I have the sine of omega t, and this just turns to cosine. So now it's the cosine of omega t plus phi, and I'm done, right? And so now I have this expression for the current, right? So if this is how I'm defining my voltage, now I have an expression that defines the current. And then to shift this, right, so that they're both in terms of sine, so I have C, so the capacitance times the peak voltage times omega, and I can change this to sine, which by shifting the phase. So this is omega t, and this would be plus phi, then plus plus pi halves, to shift the cosine, so that now it's a sine graph. Okay, so we have this expression, and if you look, I kind of have defined what phi is going to be, right? If I come back to this original function, if this is how I'm plotting my voltage over time, right? And if I'm starting here at 0 and then going like this, it's an awful sine curve. But if I'm starting here at 0, then I'm essentially saying that phi here is 0 to begin with, right? The stipulation I'm setting is that when t equals 0, phi is going to be 0. And we'll do that very often with the voltage, right? So then my voltage equation is just Vp sine of omega t, right? Because phi is going to be 0. And then this thing is just omega t plus pi halves, right? Telling us that at any given time, the current is going to be pi halves shifted difference from the voltage, right? And if I were to draw this on that little phasor diagram, we'd have the voltage here starting at 0, and then the current being shifted off from that pi halves, right? Where this is 0 and this is pi halves, and so this is the current and this is the voltage. But anyway, so we have these things, and then in time those are going to stay pi halves apart. Now this beautiful little shift and change of pi halves relationship only works for this circuit, right? It's an AC source and a capacitor. One of the ways we can kind of think about and verify this calculus is we can look at a couple of simulations. Now, so this first one that I have set up here, and maybe this has a laser pointer in it somewhere somehow. I'm not sure how to. Anyways, but if you look at this setup, right? So this is in FET. We have an AC voltage source connected across a resistor in this case, and I'm measuring the voltage across the resistor, and I'm also measuring the current in this branch. One thing that you can see here is that as you watch the little bubble electrons move in the circuit, is the current different at any place in this one loop? And the answer is that it's not, right? The current is the same everywhere, and because there's no places for the current to branch, right? So it's going to be the same in all places, right? It's not different at the voltage source, and it's not different across the resistor. And you can see in the plots that the voltage and current are exactly in phase, right? And so this kind of tells us that, like, at least when I'm dealing with a resistor, there is no shift in phase, right? There is no difference between what the current is doing and what the voltage is doing. And this is something that any of the circuits that we deal with in class, right? You can play around with in FET, you can play around with in multisim, and get kind of an idea of like how they work and what's going on. So the actual circuit that we're looking at, I've built here. And again, you can see I've got an AC source connected just directly to a capacitor, and you can watch the charges like piling up on either side of the capacitor as the current as the applied voltage across the capacitor is reversing. And now here, when you look at these plots, you can tell that they're out of phase. So I'm going to try and catch the voltage. Okay, notice, so as when the voltage is at 0 here, my current is at its peak value, right? So here, right, the current is leading the voltage. So Eli the Iceman is happy, right? It's doing what that little model expects it to do. And excuse me. And everything's in phase, right? Shifted pi halves, right? The relationship that I found in my calculus, I can see here represented in these diagrams. And then I can also kind of look and see the same thing over here in multisim. Again, notice I can pause this, and the current before the capacitor and the current after the capacitor are the same value, right? Those are not different, right? The capacitor doesn't change the current before and after it, right? But it does push the current out of phase from the voltage. And again, we can see that same relationship here in these plots, where we have voltage on the left here and current on the right, if you want to look at those magnitudes. But you can see them plotted against each other, and they are pi halves out of phase when you have just this simple circuit. And so the phase shift between current and voltage, it won't always be pi halves. That depends on the elements you have. But if you just have an AC source and a capacitor, they will be pi halves out of phase. Okay, marvelous. So I've walked you through kind of some of this basic stuff here, thinking about just an AC source and a capacitor. I recommend doing this same exercise, but this time looking at an AC source and an inductor, right? Run through the same thing. Now here, my linking equation was this thing, where I know that Q equals CV. With the inductor, it's going to look a little bit different. But there is a relationship that connects what the current is doing to the voltage, okay? And if you look at the reading, you'll find that little connector, and so you can make that relationship, and you'll find. Well, I'm not going to tell you what you'll find. You'll find what you're going to find. But anyways, hopefully this as an introduction was helpful, and I'll make a few more of these videos, and we'll kind of step deeper and deeper into this. But if you have any questions, please reach out to either myself or the TAs, and I hope you have a marvelous day.